What, in your view, do people most commonly get wrong about understanding the origins of the universe or the Big Bang?
Gosh, well, a big question to open with there, Joseph. But thanks for your kind words about the book. You know, the what we know about the beginning of the universe, what scientists have been able to find out is it all started about 13.77 billion years ago. So, you know, that's an awfully long time. And we know it started, we know because the universe is still expanding. And if you were to play the clock backwards and sort of ask what happened, and you run the clock backwards, 13.77 billion years ago, the universe would have started as a singularity, is what physicists call it, but a point of incredibly intense energy, you know, possibly a billion degrees C, and smaller than the tiniest particle that we got now. And the universe grew from that. Now, one of the things that scientists don't have an answer to, and it's really difficult to actually come up with an answer or to study it because we're part of the universe, we're in it, is what's outside of the universe. So where did the universe come from? Where did that tiny little pinprick of intense energy come from? And there are arguments, theories that people have got that what went before was unstable and it kind of collapsed to cause our universe. But it's going to be very difficult for us to actually get outside the universe, probably impossible to see what's outside, if indeed anything, and where it came from. So I think most people, certainly all scientists now, completely accept the Big Bang. There's very, very strong evidence for it from a number of routes, including radiation kind of scattered across the sky called cosmic microwave background. And the rate at which the universe is expanding, the dates of the oldest stars that we can see, all the evidence points, very, very convincingly that the universe started then as a very tiny dot and has grown ever since. And that dot it began at, that kind of intense dot, was energy with a little bit of variation in it, that energy. And that variation is what led to the sort of galaxies that we see across the sky tonight. So I don't know if there's anything that people particularly get wrong about it. There's still a lot we don't know. We don't know why it started, why it came about. We know that when it came about, it was very tiny, extremely hot, and we know that there was a mix of matter and antimatter. So antimatter, when it collides with matter, it disintegrates. There was just a little bit more matter right at the beginning when the first matter arose. And scientists don't understand why that's the case yet as well. So there's still, one of the things that I try and do in the book actually is I try and explain how science allows us to find out facts by posing hypotheses and collecting data and running experiments. So I describe how science works, but I also try and be honest about what we do and what we don't know. And one of the things we don't know is exactly why the universe started, but we know what it looked like, and we don't know why there's a little bit more matter than antimatter, but there was. And that's kind of led to the universe that we inhabit now.
No, really, really nicely said. And I think that one of the things that your book does a great job of is it's clear to me how vested you must have been in various academic disciplines, physics, a rigorous knowledge and description of the scientific method, as you just mentioned. But there, and one of the things that I found really interested was where we're talking about history and randomness, and where you kind of differentiate between a deterministic and a stochastic universe. And I wonder, first of all, stochastic is an interesting word. I wonder if you could just, I guess, kind of define the two and then kind of just talk about the kind of differences between them and I guess the evidence for each principle.
Stochastic is really a word that describes something that's got random elements to it, so chance elements. So stuff that's not entirely predictable. You can't exactly predict what's going to happen. Whilst deterministic means that you can predict exactly what's going to happen in the future. And if you find the right mathematical equations, you could predict indefinitely into the future with the right computing power and what have you. And now there are some physicists who argue that the universe is deterministic. So what that means is that if we were to do an experiment and we were to set up the universe in exactly the same way that it began 13.77 billion years ago, and we ran it forward, you and I would be sat here having this conversation. And there are theories like sort of metadeterminism and what have you, where some physicists argue that that's the case. Now, if that's true, that's really interesting because it means that all of those things that we think are free will, that we make decisions about, aren't free will, and free will is just an illusion. Now, the flip side of that coin is that the universe has random elements to it, so there's chances involved. And that means that if we were to do that experiment again, create the universe exactly as it was at the beginning, that incredibly that small pinprick of incredibly intense energy in exactly the same way it was at the beginning, we ran it forward, then we wouldn't necessarily be here. The Earth might not be here. If the Earth was here, humans might not have evolved. There might still be dinosaurs wandering around, or life might not have got started. There may be no moon. All of these sorts of things. And so, if there are chance elements, I think one of the questions you have to ask is where does that randomness come from? And because we some bits of the universe we have equations, we could describe the behavior of it pretty well. We can describe the orbits of the planets around the sun pretty well. We can describe the tracks that comets make across the night sky when they're going to come close to Earth and what have you. So there are some things we can predict pretty well that are pretty close to deterministic, if not exactly deterministic. But free will and life and what have you, many biologists would tell you that the genetic mutations appear to be random, they appear to be stochastic, so occurring by chance. So where does that come from? And the one thing that physicists and biologists and lots of people would say does look to be random is the behavior of very, very small particles in what's referred to as quantum mechanics. And what that means is it's impossible to pin down all properties of a tiny particle like an electron or even an atom. So you might be able to measure something about it very accurately, but then you can't tell anything else about it. So you might be able to say how fast it's going, its velocity, but you don't know where it is very accurately. And so that's kind of one area where randomness exists. And so the physicists who argue for determinism believe that at some point we'll decide that isn't random and we'll be able to predict it accurately. But all the evidence we've got at the moment is it's got a random element to it. It's stochastic.
Will we ever get a definitive answer to that question?
So that's a very good question. There are some hypotheses out there that some physicists have put up that kind of allow us to take the randomness that we see at the quantum level and argue that it's deterministic. Now, one of those theories is something called the many worlds theory. And that says that everything that can happen does happen, but we only experience one reality. And there's a kind of parallel universes. I know it sounds like something out of the films, doesn't it? But there's parallel universes where other outcomes are happening. And each of these outcomes occurs, but we only experience one of them. The problem with that is it's untestable. So it's not a particular. It's an interesting thought experiment, but it's not a testable hypothesis at the moment. Will we be ever able to test it? I mean, never say never, but at the moment it's very difficult to see how we can test it. So, in assuming that, and as science finds out more and more information, and we kind of get better at interpreting the data that we've already got, it's possible that we may come up with some new theories or some new experiments that allow us to say actually the quantum realm is predictable, is deterministic. But all the evidence we've got at the moment suggests that's not the case. So my hunch is that randomness is real, that we're not going to be able to explain it away as deterministic, and that means that the universe is stochastic, and that means that if we were to rerun the clock again, we wouldn't necessarily be here.
Yeah. And just in terms of, I guess, of just a novel thought experiment, if in fact the determinism theories were true and that we could predict what Joe or Tim in 10 years would be having for breakfast, and they would in fact be having that, what kind of, I guess, implications might that have? Because that's the kind of questions that I've been I've been thinking about.
Yeah. No, I mean that's interesting. So one of the roles of science is to be able to predict the future, and that would be useful if we were. So I guess there's two parts to the question. So first of all, if we were able to decide the world is deterministic, on our day-to-day living, it's probably not going to impact you and me very much, to be honest. And the reason for that is, say we discover it's deterministic, actually the computing power to, even if we, if it's deterministic, it means there's a set of equations that exist that would allow us to predict accurately everything that happens into the future. But we'd need to find what those equations are, and those equations would probably be tracking every particle in, our bit of the universe, or even the entire universe. And the computational power to do that would probably have to be as large as the universe itself. So we wouldn't probably be able to say, what we'll be having for breakfast in 10 years' time. Although I always have granola, a banana, and yogurt, so I'm pretty confident I can predict that anyway, without the universe being entirely deterministic. So who knows? Uh, you know, bananas might be unavailable that week, so I might have to have something different. So, but on a more serious note, if we get, as science gets better and better at making accurate predictions of systems, that can be useful because it can help from all sorts of things, like the development of self-driving cars, to better predictions of the weather, to probably better understandings about the impacts that we're having on our natural environment, things like climate change, modifying natural ecosystems. We might be able to better predict the consequences of that. And if we are able to better predict the consequences of that, we could also, perhaps come up with better ways in identifying which interventions are most likely to work in our favour, sort of reducing the negative impacts.
Of another tangent, you, in terms of, I guess, stochastic events, you yourself in your life, I guess, had what appears to be a number of stochastic events. Perhaps they were predetermined, but to my knowledge, are involved run-ins in Africa, bouts of malaria. What were kind of some of the, I guess, notable things in your life that happened that kind of, I guess, led you to writing this book?
Yeah, so I do have a bit of a personal sort of story here, personal narrative. So, I was brought up by great parents, and but was sent off to church and to Sunday school as a kid, Church of England. But in my late teens, I decided I didn't believe in God and was an atheist, and actually that was around the time I really became a science geek. Back then, it wasn't trendy to be a science geek. It is now, but anyway, never mind. So I fell in love with science, and what science could tell us and how we used it to find out facts. And actually, I had a place back when I was 18. I had a place to go off to university, or 17, I guess, to go off to university to study maths. But then someone came to our school and talked about a year off they had, and they'd gone off to Africa. So I went home and I told my parents, I said, I'm going to have a year off. I'm going to go to Africa. I like the idea of trying to play around at being Tarzan, I think, to be honest. But my parents said, well, you're not staying here. And I said, no, I know I'm not. I'm going to Africa. Anyway, cut a long story short, I got very lucky and worked with an organization called Project Trust. And I went and taught in a school in Africa. Halfway through that year, I remember going for a walk and stopping to watch some wildlife. There were some antelopes and gazelles. And I decided I wanted to be a biologist. So I wrote to my parents, who probably thought, oh, God, there goes our future. We'll be supporting him for the rest of his life. He doesn't want to be a mathematician. He wants to be a biologist. But I did biology, loved it, really enjoyed it. And then at the end of my degree, I went off to Africa again. And this time I developed malaria, and I nearly died. So the doctors, when I came round, said, if I hadn't got to hospital, the next attack would have probably killed me. And so once I got better from that, once I recovered, I thought, well, what do I want to do with my life? I've been dossing around, traveling around Africa every opportunity I get, working on these projects, but I haven't got any aim. Life's good, but I should come up with an aim. And that was when I decided, by the time I lay on my actual deathbed, I kind of wanted to have an idea of how the universe worked. So I started reading incredibly widely and broadly and thinking deeply. Sort of 35 years later, I ended up writing this book. So I think it feels to me in my personal narrative that those two events, going for a walk or going off to Africa and then going for a walk and looking at the gazelle, and getting malaria were kind of two key events in my life that were, um, you know, happened by chance, perhaps, and but they did kind of change the course of my life in terms of what I wanted to do. And perhaps if I hadn't got malaria, I would be Tarzan. Who knows?
I think that that example highlights a really good quote of yours that I liked in the book. And you said, I decided that by the end of my life, I wanted to have a good understanding of why I existed and why I developed a personality that would soon blink out. And I think that that example gives a good illustration of ways in which, I guess, genetics and environmental factors kind of shape up. So do you kind of look at those two, that as their interaction as something that I guess shapes up individual personalities and also I guess what we would call a destiny?
So I don't know if I'll go down to destiny, but yes, absolutely, you're right. So towards the end of the book, after I've kind of gone through chemistry and how chemistry works, how the format, beginning of the universe and physics, and a bit about chemistry and how chemistry works, how molecules interact, then through the formation of our solar system and the Earth, and then emergence of life. And then I get on to humans, and one of the last chapters is absolutely about that. You're right. Thank you for that flattering comment on that quote. But in that one of the last chapters, I do think about and discuss what science can tell us about why we have the personalities that we do, and there are three elements to that. So the first element is our genes and the genetics we've got. And it's very clear from a lot of biological studies and genetic studies that genes play a role in determining whether we're, outgoing, how introvert we are, the things that we're drawn to in terms of things that we like, also things like sporting ability and what have you. So genes contribute a lot, but they certainly don't determine everything. And the environment that you experience is also incredibly important. And the genes and the environment can interact in all sorts of complicated ways. And so, if I was born into a household, two loving parents in Cambridgeshire in England in the 1960s, 1968, if I'd been, born in Victorian London, it may have been a very different outcome, even if I had exactly the same genes. And so part of it determines what opportunities the environment give you, but also you kind of all eventually start to select your own environment a little bit. I don't like dance music, so I don't have much experience of dance clubs. So whether that's genetic or not, I don't know. But I was drawn. I wasn't drawn into that scene, and so. But I did love science. I loved reading throughout my life, and so I kind of sought out environments where I could learn more about science and what have you. But chance also plays a role. And chance plays a role both in what's known as developmental biology. So our brains is each wired slightly differently. Some of that's genes, some of it's environment, but some of it's just sort of chance, as best as we know, as best as biologists know. So yeah, all of those things play together to determine our personalities. And our personalities, of course, do change a little bit over life. I was quite a shy child, but I've become probably more outgoing and more gregarious as I gotten older.
And I'm thinking about it as kind of a dance between the genes that we have, the as you said, the role of chance, and also the environment. And in terms of just shaping up our personalities, do we know kind of who takes, I guess, the lead in the dance? Does it switch depending on what song is being played? What's the kind of way you're thinking about that?
It certainly is. They can feedback and influence one another, and that's kind of what one of the things that I talk about is we learn what we like, and what we like is kind of past experience, but possibly also our genes. Because if you're genetically happen to be good at something, you're probably going to enjoy doing it. So I don't enjoy tennis very much because I don't think I've ever won a tennis game. But if I had won games when I was younger, I might have enjoyed it a little bit more and got into it. However, I did enjoy maths and science because I did well at it and I kind of got those feedbacks from school. So I don't think I think I don't think saying one is more important than the other is quite right. It's the fact they do dance together. A dance is a really good analogy, and they feed back and they can influence one another. So it's quite a dynamic process. But the other thing is the environment is incredibly complicated. So I talked about getting malaria and feeling, I can't prove it, but my personal narrative is that getting malaria made me decide I wanted to write this book. And, that was what or wanted to understand existence and eventually write this book. And that's kind of what drove me forward to do that. That's kind of one relatively short event. It was an infected mosquito biting me, and it carried the bug that causes malaria, Plasmodium falciparum in this case, and falciparum, and I ended up developing malaria. Now, that's a very small kind of environmental impact, right? But I feel it changed the course of my life. And for scientists to be able to really prove those sorts of things, you need to find a large number of people that have experienced a particular environmental event and others that haven't, and hopefully they're randomly matched for all their other characteristics. And then science can ask the question about, well, does getting malaria when you're an 18-year-old or whatever, a 20-year-old, however old I was, have the opportunity to change the course of people's life in the way that Tim claims happened to him. So I know, and I'm completely honest in the book, that in that bit of the book, that working out exactly what caused one individual to be the way we are is really quite difficult unless we get a very, very good mechanistic understanding of everything that kind of goes on in our brains. And we're a very, very long way. Scientists are a very, very long way from getting to that point.
You don't have an identical twin?
I don't have an identical twin. No. Yeah, I have a sister, but we're very different. We get on, but we're very different.
Amazing. I would love to kind of just touch on some things I found just incredibly interesting in the book, and I'd love to kind of speak just about the evolution of life. And one of the things I think that you do a really good job of describing is the incredible and rare conditions that were kind of, I guess, needed, I guess, for the emergence of life. And I wonder if you could just kind of talk to, I guess, the critical steps and the conditions that were necessary just for the emergence of life to actually happen, because I found this so fascinating.
First of all, Earth is the only place that we know of where life has evolved. That doesn't mean it's not incredibly common in the universe. We just don't know. It may only have happened on Earth, or it may be really quite common. And the reason is we've explored such a tiny, tiny corner of our universe. We've been to the moon, we've been to Mars. Well, people haven't, but we've sent rovers to Mars to wander around. So we haven't found life on those two bodies. Life may have existed on Mars. Unlikely that it does now. So Earth is the only place we've got to study it at the moment. And biologists have got a definition of life now. And from that definition, they're able to sort of work back, and they're able to look at simple forms of life. And life needs to be able to really do three things. It needs to be able to make copies of itself. And the kind of key chemical that makes copies of itself is called DNA, or deoxyribonucleic acid. And and making copies of itself, or any chemical that makes a copy of itself, is known as autocatalytic. So you sort of have one molecule of A and say a few of B. A would be able to create new copies of A out of chemical B. And so that's one thing that life needs to be able to do, is sort of be able to make a chemical, being able to make copies of its life. Second, it needs to be able to use energy to do that, and that's referred to as metabolism. And biologists are pretty certain that the first life used chemicals we use food. We have to rely on other animals and plants in order to stay alive, to get our energy. But some bacteria run off chemical reactions gained from quite simple inorganic compounds, so hydrogen sulfide, for example. And that can be generated from volcanoes. And so one of the arguments that people make is, one of the things that we probably needed for life to get going was volcanic activity. And Earth's got quite a lot of volcanic activity, But there's evidence of volcanoes past on Mars and also on Venus. So it looks like volcanoes happen reasonably frequently. And then the third thing that you need is to be able to kind of lock up your metabolism driving chemical reactions and the autocatalytic reaction within a membrane. And a membrane is like you were made of about 30 trillion cells. Each cell has a membrane around it, and that membrane's made of a type of fat, kind of lipids. A lipid bilayer is what it's called. And so it turns out it's very easy to make membranes. It turns out metabolism is probably reasonably easy. Certainly autocatalytic reactions occur, and once they occur, they really can take off because you end up being able to make a lot of copies of a certain chemical, under the right conditions, as long as you've got the right ingredients to do so. The challenge that life researchers have really got is bringing those three things together and working out how metabolism, autocatalysis, so autocatalytic reactions, and a membrane all came together. And we don't know the conditions under which that happened. There are some very good theories out there. So the two predominant theories are: one, this occurred in sea vents where volcanic activity comes to the bottom of the sea, and you get lots of heat and lots of chemicals coming in, and then in kind of little pores in rocks that were kind of quite high in minerals. That's where life could get going. That's certainly plausible. The other place is on what known as geothermal plains, and that's places like Yellowstone National Park, where volcanic activity ends up sort of causing a bit of a hotspot on the Earth's surface. And again, that provides you with the energy you need, and you can end up with kind of fresh water building up there, and lots of organic chemicals. And so the organic chemicals that life needs, lots of carbon-based chemicals and what have you, and many of those, including many of the key building blocks of life, are found on meteors, actually, and meteorites when they hit the ground. And so it looks like quite a lot of the building blocks of life, but probably not life itself, are very easy to make throughout the solar system, throughout the galaxy, presumably. And then they're brought to Earth, or they're brought to a planet on meteorites. And as long as there's volcanic activity and enough water and the right temperature gradients and what have you, perhaps a few other things we haven't identified yet, then it may be relatively straightforward for life to get going. We don't know that. Science doesn't know that. But, that's one of the things I certainly discuss in the book about what's needed for life to get going. And, was the Earth particularly unusual when it got going? There may be one or two unusual things about it. We have a larger moon than other planets of our size within the solar system, and certainly a large moon given how close we are to our sun. That's quite interesting. That was caused by a collision of the early Earth with a planet called Theia. Very good evidence for that. The moon may be key for life. It created tidal cycles that may have helped life get going as well. So a lot to learn there as well. You're right that science doesn't have all the answers on how life got going. Made astonishing progress. Chemists and biochemists and biologists have made astonishing progress in this area in the last few decades. And I do hope that in the coming decades, we are actually able to make life in the primitive life in the laboratory, but we're not there yet.
Yeah, and you mentioned some really interesting, I guess, geological events there. And just in terms of asteroids, volcanic eruptions, how would these, for instance, have influenced, I guess, the diversification and I guess the development of life on Earth?
So all of life on Earth at the moment, and all of life life that we've ever found and looked at, uses the same genetic code. We all use DNA, and we always the cellular machinery always uses DNA in the same way to make things called amino acids that are then stuck together to make proteins, and they're kind of the drivers of life. And so because we all use that, we can kind of build a tree of life, and we can kind of go back to the root of that tree of life. And it's an organism that scientists have called LUCA, the last universal common ancestor, that probably lived about 3.8 billion years ago. We don't know what it looked like exactly, but we know it used DNA, and it used the genetic code we've got now. And then life, so what life's very good at is finding resources to use. And so life, it probably started, as I said, using simple life would have been using chemicals coming from volcanic vents or on volcanic plains. But it would have spread and it would have diversified and it competed with itself and as it diversified, it would have found new chemical sources to use. Eventually, it learned to use light and photosynthesis evolved. Some of those routes to photosynthesis, some types of photosynthesis created oxygen as a byproduct. Oxygen was poisonous to most forms of early life, but then some other bits of life started to be able to use it. Eventually, things like predation got going, and predation ended up with a bacteria living inside what's known as a eukaryote cell. That bacteria and the eukaryote, over time, they evolved to have a mutualism which underpins all of the cells that make up you now. Each cell's got lots of things in them called mitochondria. These mitochondria are the powerhouses, but they originally come from bacteria. But on this journey, life, it spread, it diversified, and in our branch of the tree of life, it got more complicated with lots of cells started working together. Multicellular life came about. As I said, you're made up of 30 trillion cells. So am I, and so is everyone. And it got going. But on its journey, every now and again, there would be a sort of catastrophic die-off caused by major extinction events. And so the extinction event that everyone's most familiar with is the extinction event that killed off the dinosaurs 66 million years ago. And that was caused by an asteroid crashing into Earth. And the resulting long dark winter killed off a significant number of animals, not just the dinosaurs and plants, but life rebuilt afterwards. That's one of sort of 5 big extinctions. We might be in the 6th big extinction now. People argue for that. The biggest extinction was called the end Permian extinction, and that might have kind of killed off about 90% of life. And we think that occurred due to several million years of intense volcanic eruptions that led to something called the Siberian Traps, which are an area the size of Australia which is kind of covered in basalt. And that, life nearly died out then. There have been other periods when life has really struggled to survive, but it has always hung on. We're now in what some people describe as a 6th great extinction. What's really unusual about that is it's not being caused by volcanic eruptions or asteroid impacts, or something like that. It's been caused by us, and we've evolved to be able to drive other life forms extinct, and that does make us an unusual and an interesting species. We're probably not doing ourselves much good by driving other things extinct, but it's what we are doing anyway.
Yeah, I think that kind of just goes to show as you write about in the book, the kind of the very specific alchemy that is needed to survive, and I guess just kind of and for life to come about. And I'm just wondering just about some other, I guess, fundamental forces that also would have needed to be present. Things like gravity, electromagnetism, nuclear forces. What role are they also playing in this process?
So they're fundamental. They're correctly called the 4 fundamental forces. And they all emerged within the first fraction of a second of the universe, with gravity appearing first, then the strong nuclear force, then electromagnetism, and the weak nuclear force. And each of those forces was necessary for life to come about, but they had to take the right strength. So what I mean by that is each of those forces has a strength. Now, if gravity was a bit stronger, for example, you wouldn't be able to jump as high as you can. So gravity is an attractive force that brings objects with mass closer to one another. It attracts them towards one another. And so that's one of the forces we're most familiar with, because it anchors us to the earth. And it was the first one that was properly described by scientists when Isaac Newton watched apples falling from his tree. He thought, why do they fall together? So he kind of came up with the first theory of gravity that was refined by Albert Einstein. But then, a host of other scientists discovered electromagnetism. So that's a force that means why you kind of can't, when you walk into a wall, you don't go through it and you bounce back. and it's why molecules and atoms join to one another to form larger, why atoms join to one another to form larger molecules, but also why electrons spin around in orbitals around the nuclei of atoms. But right in the middle of the atom, so atoms are sort of a fundamental to life on Earth. Right in the middle of atoms are things called protons and neutrons, and those protons and neutrons are made up from even smaller things called quarks. And the quarks join together through the strong nuclear force, and then the protons and neutrons join together through the strong nuclear force. But then there's another nuclear force called the weak nuclear force, which sometimes means that some atoms can show to do radioactive decay and they break down. Now, each of those forces is fundamental to life on Earth. If we didn't have the strong nuclear force and it didn't take the right strength, we couldn't form atomic nuclei, protons and neutrons. If electromagnetism was a different force, we wouldn't be able to get the huge variety of molecules and atoms of different elements that exist on Earth at the moment and throughout the universe at the moment. And if the weak nuclear force didn't happen, we couldn't have the sun. We wouldn't have stars burning bright. It's absolutely fundamental to stars burning bright. And as I said, if we didn't have gravity, we wouldn't be able to form planets and kind of have matter clumping together, which is necessary for life as well. So each of those forces takes a value, and if those forces were just a little bit different, then life couldn't exist. So we needed them to be finely balanced. Now, some people, it's quite interesting, some people say, well, the fact that those forces just take exactly the right value, that's kind of a bit freaky, isn't it? That must mean there's some deeper meaning to what's going on. And some people have used it as arguments for the existence of gods and deities. However, the counter to that is, but if those forces weren't right, we couldn't be here anyway to observe the universe. So it's no surprise that they're just right for us to be here, because they have to be just right for us to be here. It's not, you can't interpret anything deeper than that. So but they are absolutely fundamental, and they're the stars of the book, to be honest. The fundamental forces. Without them, we couldn't be here, and it's amazing what understanding of the fundamental forces that scientists have built up. They're still not quite, they don't understand how all the forces interact perfectly. So they don't know how gravity interacts with electromagnetism and the strong and the weak nuclear force as well as they would like. And that's kind of one of the big challenges that particle physicists, are still trying to solve.
And I don't know, Tim, if you're much of a betting man, but what would the actual odds be to have all of those forces and to give rise to the fact that, you and I are here today? Is there a kind of, has someone quantified it in terms of an actual probability of us being here today?
No, because we don't know enough about, as I said, why the universe began, and we don't understand enough about why the fundamental forces, took the values that they do. It's possible that other universes formed and had very different forces and, didn't stay in existence for very long. What we do know from lots of simulations that scientists have done and mathematical models is that you change the forces a little bit and the universe would look very different to what it is now. So I would, I don't bet very often, but as a betting man, if I was a betting man, I wouldn't put a lot of money on it, I think, because we don't know yet. But I mean, I think one of the things I really kind of want to come out of the book is just how amazing science has been at uncovering what we know about the universe. We don't have all the answers. I mean, I think that's a really good kind of question you've asked. Kind of lets me say that. But what we do know is amazing. I mean, it's absolutely stunning how far science has brought us in terms of our understanding of how we've got here over the last kind of couple of centuries, and it's absolutely staggering. I mean, there are each chapter there's kind of what research that could fill libraries about it. So I only scrape the surface, but I do at the end of the book kind of point interested readers who thought, well, that's interesting, I'd like to learn more, to other books that they might be able to go and read and sort of further their journey. But I also hope, I mean, anyone can be a scientist, to be honest. If I can be a scientist, trust me, anyone can. And I just hope to be able to infuse people that, science is amazing. It's not, some of it, some mathematical equations are very complicated. Some of it's kind of very abstract. The quantum, what goes on at the quantum level is kind of difficult to get your head around first of all. But if you persevere, you can get there. And science is all about curiosity and testing. It's about being imaginative and coming up with imaginative experiments to kind of test hypotheses and ideas that you've got. So, I am a science junkie. I love it, and I'm just amazed at how much it's told us. It really is an astonishing journey, and I've I've tried to outline that journey in the book, but hopefully I succeeded.
Yeah, and I think it's, as you kind of talk about, advances in things like, I guess, like the Large Hadron Collider. These have all been incredible events, and it really does pay tribute, I think, to the scientific method, which kind of leads us to, I guess, where we are here today, right?
That's right. No, and the Large Hadron Collider is the world's largest machine. It's used to accelerate tiny particles to close to the speed of light and then collide them, and then huge detectors to work out what what new particles are found. And one of the reasons, the main reason the Large Hadron Collider was built was to search for something called the Higgs boson, which was a particle that physicists had predicted existed, and Peter Higgs was the guy, I think that was his first name, who predicted the existence of this particle. And they built the world's largest machine to look for it. And it was where the equations said it should be. They found it. That's just how good science is, to be able to predict, or physics is, to be able to predict that a particle exists, and then to be able to go and look for that particle and it's there. So, I mean, that's an amazing triumph of science. And, there have been similar triumphs of what science has been able to to achieve in chemistry. We're neuroscientists are starting to work out how the human brain works. A lot of artificial intelligence is based on the structures of within the human brain. Biologists have been able to understand how the immune system works and use that understanding to help treat diseases. It's absolutely amazing. The modern world is built on the back of what science has achieved, and I mean, given that, it's always slightly, frustrating when you discover people who are so distrusting of science, and it is very powerful. So, maybe that's one reason, but also sometimes it's hard. But it's not science that's to blame. It's up to us as people to work out how science should be used, and we should be using it for good, and encouraging people to use it for good, and punishing people who use it for bad.
Sure, sure. And I guess on that note, one other question that I would just love to kind of ask you, a bit more abstract, but one to get the imagination going. What are the current scientific theories about the potential of extraterrestrial life? And the reason why I ask is just because we just painted an incredible tale for just how rare life is on this planet, and the complex conglomerate of events and forces that have to exist for us to be here. I'm curious, what your kind of take is on that.
As I said, Earth's the only place where life that we know has come about. It's really proliferated. Once it started, it's spread, and it's everywhere on Earth. I mean, it's done amazingly well. Is it elsewhere in the universe? Now, my suspicion, the universe is vast, and that's the other thing you've got to realize. There's trillions of galaxies. Those galaxies can have billions of stars and trillions of planets. It's absolutely huge. It takes light to leave Earth to go to the center of our galaxy. About 26,000 years. So that's how big it is. And light's the fast. Light's the upper speed limit to the universe. We've sent, just to give you an example of how big it is. The Voyager 1 is it's a satellite that humanity built in the 1970s. Set it off into space. It's the furthest object from Earth. And it's still moving away from Earth. If that had been traveling since the beginning of the universe, it would have only made it about just over halfway to the next galaxy. I mean, the universe is staggeringly large. So we've only explored a very, very tiny corner of it. And it's possible that life exists elsewhere in our solar system. Some biologists and astrophysicists have argued that life could exist on some of the moons of Saturn and Jupiter. We haven't been able to go there, but they're pretty confident there's liquid water under big ice layers. It may only be simple life, but it could be there. There's nothing to say the Earth is so fantastically unusual that that it's the only place in the universe for life to have started. And my guess is life starts fairly frequently. But even if it's only one planet in each galaxy, there could still be trillions of planets with life on it. I mean, that's how big the universe is. The problem we have is so big we wouldn't be able to find them, right? Because they're so far away and any signal would be coming through would be weak. Once life gets going, as I said, life on Earth has had several scares when it's nearly been wiped out. In order for it to kind of develop to the sort of level where you've got intelligent life, like humans, it's going to take time. It's not going to arise overnight. It took, the best part of 4 billion years for intelligent life to arise, or life as intelligent as humans to arise on this planet. So it's a long time. And on that time scale, we still don't know enough about whether planets remain in a sort of stable enough configuration, a stable enough orbit that that life could thrive over that long period. So we don't know the answer to that. But the universe is so large. I would be amazed if I was a betting man. I would bet on this. That there is intelligent life on other planets. It may be so far away we may never communicate with it. Ever since we've been sending out radio signals, which is kind of Marconi's first phone call, that's been traveling through space. If it, got picked up by someone else and then sent back, it's going to be traveling 50 odd years out, 50 odd years back. It's only a few thousand star systems that signal would have reached. So even the kind of noise that we're making and sending out into space has only traveled a fraction of a distance. So, the chances of other alien civilizations and knowing that we are here is they'd have to be very close by to know that. So so I think life is quite common. I'm as a betting man, I don't know. My guess is life gets started quite frequently. I suspect that intelligent life is rarer, but I very much doubt we're the only intelligent life in the universe. But we may never know. We may never know.
Well. I mean, I don't think there's many questions I could follow it up with. So, yeah, that's you've certainly, I think, done a great job there of both painting an incredible history of our time. And as I said to you before we started recording, most people they write narrow books. Or books about niche topics. You've taken the journey of writing, just this incredible book on everything, um, which is just such a brilliant read, and I highly recommend it. So Tim, tell these guys where they can connect with you, where they can get the book, and if you have any other closing messages, send our audience to check it out.
Yeah, well, so the book is called The Universal History of Us. Oh, there you go. You can see it on there. A 13.8 billion year tale from the Big Bang to you. Published June the 13th. Be available on in all good bookstores. You can buy it on Amazon. You can buy it from the Penguin website. It's Penguin who's publishing it. I've recorded the audio book, so if you if you like the sound of my own voice, you can get even more of it. It's published by Pegasus Books in the US, and the title there is The Science of Why We Exist. So it's got a slightly different title. You can find me on Twitter, Prof Existence, if you wish, and you can find my website. I'm based at Oxford University. I hope you enjoy the book. It's such a broad topic that I did do as much fact checking and get people to read it. I'm sure there's the odd thing I got a little bit wrong. Don't be too harsh on me if that's the case. But I hope it enthuses people to engage with science more than anything, and I hope they enjoy it. And it's been wonderful talking to you, Joseph. Thank you so much. I've really enjoyed it.
Oh, Tim, my pleasure. And before we go, I just got one last question for you that we sign off all our podcasts with, and that is for Professor Tim today. What makes your life worth living?
you know, I believe I'm only going to live once. I don't believe there's any life after it. So I figure I might as well enjoy it. And I enjoy, and so yeah, I choose things that I enjoy. I am lucky. I enjoy my job. I'm a professor at Oxford University. I like doing science. I'm currently head of department, but my sentence ends soon. That will be a relief. My dog Woofler features heavily in the book. I love taking him for a walk. But most of all, it's probably my wife Sonia and my family that give me real pleasure. I love hanging out with them all, and we just have a great time. I think if there's a message that science tells us is enjoy your life and don't make other people's lives miserable. That's what I'd say.
Sure, sure. Well, Tim, this was such a pleasure. Thank you so much for coming on.
Fantastic, my pleasure.